Hi everyone. So in our last video, we focused on describing the domain of a function. So we learned that the domain of a function is the set of all possible inputs for the function. And so we saw a variety of different types of answers that could be, right? So we saw like a table where the domain was just 3 specific numbers. We also had domains that were things like all real numbers besides 5 or all real numbers less than or equal to 2. You know, we had all sorts of different types of groups of numbers. So when I say the word set, just think of that as being like a group of numbers. It's kind of like a fancy math word, but it really just kind of means a group of items. So we're trying to describe all these different sort of groups of numbers that are our domains. And so what we're going to be doing in this video is learning some notation that allows us to, rather than having to describe everything in words, gives us like a more concise way of describing the domain. So in this video, we'll basically be learning new notation that is used to describe sets of numbers. So the stuff that we're going to be talking about in this video is technically supposed to be things that you learn in the previous math class before this, but I found that a lot of students either never learned it or are a little rusty on it. So I just want to make a video to basically review this notation. Okay, so before we get into what the notation actually is, I want to kind of bring up a couple of examples of finding the domain again, just so that we have some sort of like motivation for the kinds of situations where you use this notation. So when you have a function that is described by a table, and I'll write an example down in a second. So we talked about this a little bit last time, that when you have a function described by a table, the domain is only the numbers on the table. And so the way that I'm going to write that down here is that the domain is a finite set of numbers. And I'll explain a little bit more what I mean by that in a second. So the domain is a finite set of numbers. So what does the word finite mean? Well, it's the opposite of infinite. Right? So finite means it's a number that you could count, right? Like 5 is a finite number, 1,000 is a finite number, 1,000,000 is a finite number. As long as it's not infinity, it is considered a finite number. So to give an example, let's say we had the function defined by this table. So we have -1, 7, 10, and 4, -3, 8. So we did an example kind of like this last time, and we said that, okay, the domain is only the numbers, numbers starts with an N, not an M, the numbers -1, 7, and 10. That's it. If that is the only information given in the table, those are the only numbers in the domain. You can't kind of fill in the blanks between them and guess. That is literally the only numbers that you're allowed to plug into your function. And so that's an example of a finite set of numbers. It's just 3 numbers. And so this is not going to come up as much. So this is basically all we're going to talk about this kind of situation, just because it's not super important. But if you have a finite set of numbers like this, the way that you can describe that is using something called set notation. So in order to describe a finite set of numbers, so I'm just going to write it down here for this example. You basically just do these kind of curly brackets, and then you just literally list the numbers inside the bracket. So whenever you see these curly brackets, think of that as basically just introducing, here's a list of numbers. It's just like a fancy way of kind of presenting a list of numbers. So let me kind of summarize that as kind of a more general case. So to describe a finite set of numbers, so let's say that those numbers are x1, x2, all the way up till xn. So here n just represents some number, right? We're trying to be general, so I don't know how many numbers I have, but in this case, for example, n was 3, right? We had 3 numbers. So if you have a finite set of numbers, x1, x2, x3, x4, etc., up to whatever, you can use set notation. And you basically just put a curly bracket like we just said, and you just list your numbers inside those brackets. So like I said, that's not super important, but it is worth mentioning, at least to kind of contrast it from the other examples we'll see. Okay, so table, finite set of numbers in the domain. What we'll see is that when we look at functions that are defined by now formulas, generally speaking, your domain is actually going to be an infinite set of numbers. So for functions described by formulas, the domain, you could cook up some weird exception to this, but in general, the domain is going to be, I'll say, is generally an infinite set of numbers. Okay, so let's I think by looking at an example, it'll become a lot clearer like what I mean by that. So let's say that we have the function, let's say g of x is equal to the square root of x minus 3. So I think we did this exact example in the last video. If not, we did something really similar. And so what we figured out is that the domain is all numbers, I'll say all real numbers, specifically all real numbers that are greater than or equal to 3. And I'll remind you how we can tell that. Okay, so how can we tell that it's all real numbers greater than or equal to 3? Well, remember that when you have a square root function, really the only thing that can go wrong is taking the square root of a negative number. So we need to make sure that whatever we're plugging into this makes it so the stuff under the square root, that the name for that again was the radicand, we want to make sure that the radicand is positive or 0. And so if we plug in a number like 3, well, if we plug in 3, we'll get 0, and that's fine. If we plug in 4, we'll get 1, and that's a positive number. And so as we plug in bigger and bigger numbers, we'll continue to get a positive result under the square root. But as soon as we plug in a number that is less than 3, so like 2, for example, if you plug in 2 for x, you'll get 2 minus 3, which is negative. And so that's how we can kind of determine what the domain is. And by the way, in the next video, we'll actually kind of do that process using algebra. So that might, if you find this a little bit wishy-washy, this idea of plugging in numbers, don't worry, in the next video, we'll make it a little more concrete. Okay, so what do I mean when I say that this is an infinite set of numbers? So the set of all real numbers greater than or equal to 3, that is an infinite set of numbers. So what do I mean by that? Well, basically, if you think about what are all the numbers greater than or equal to 3, there's a lot of them, right? So this includes, if you're trying to kind of brainstorm what are some, numbers that are greater than or equal to 3, you might think of, 3, 4, 5, 6, etc., right? You might just think of those kind of nice, clean integers. But if we're talking about all numbers greater than or equal to 3, that also includes all the numbers between these, right? So this is also going to include all numbers that are between. And so what do I mean by that? I mean numbers like 3.1, 3.01, right? That's a number that is still a little bit greater than 3. You could have something like 4.7. You could have something like 4.999. You could have something like 5.2. You could have something like 100.1273529. Like literally any number that you can cook up that is greater than or equal to 3 is in the domain, right? Because the only thing that can go wrong is getting a negative under the square root. So as long as we're plugging in a number that is bigger than or equal to 3, it's going to be fine. And so that is why I say that this domain includes infinitely many numbers, because you can put as many different decimals as you want. As long as your number is greater than or equal to 3, it's in the domain. And so we're not going to be able to use this kind of set notation in this situation, right? Because the set notation means you literally list out every number. And if you were to try to list out every number that is greater than or equal to 3, well, I'll tell you, you're not going to be able to do it. You're going to run out of time because there's infinitely many numbers that are greater than or equal to 3. So we need a notation that isn't just listing out numbers. And so what we're going to use in this type of situation is something called interval notation. So to describe an infinite set of numbers, we're going to use what's called interval notation, and that's what we'll talk about on the next page. So basically, you're going to use interval notation in these situations where you're kind of cramming in all these numbers, like every single number in between two numbers or bigger than a number, something like that. Okay, so I have this kind of table that I want to fill out with some different sort of situations that will arise. And by the way, in the rest of this video, we're not actually going to be talking about domain. We're just going to be focusing on describing sets of numbers. And then in the next video, we'll kind of put all the pieces together and kind of start to finish do problems where we start by finding the domain and then we put it into interval notation. But for now, the focus is really just understanding how interval notation works. Okay, so I want to fill out this table, and for each of these things, we're going to take a description that is in words. We're going to turn it into an inequality. We're also going to write it on a number line, kind of sketch on a number line, and then I'll show you what interval notation looks like. Okay, so let's say that we have a number, or we're saying x, some number is between a and b, where a and b just, are two numbers. Maybe they're 3 and 7. It doesn't matter. They just represent two numbers. So how would you write that as an inequality? Well, you would say x is between a and b. Okay, so how would you draw this on a number line? Well, if you had two numbers, a and b, and you kind of put them on your number line, I put this open circle here, and we'll come back to this idea. Notice that on the inequality, I just said I put the symbols as like less than or greater than. I didn't put the equal sign. So basically everything on this table, we're going to assume that the endpoints are not included, and then I'll tell you afterwards how we do it when they are included. Otherwise, this table would be super long. So we're just going to start by not including the endpoints. So if you are trying to describe all numbers between a and b on a number line, it would look like this, right? You would say, here's my first number, here's my second number, and then I'm shading in all the numbers between. So, again, if say that a is like 3 and b is 7, that means we would have the number 4, 5, 6. We would also have 3.1. We would also have 4.99999. Like every single number that you could imagine cramming between 3 and 7, we're shading those in. That's what the shading kind of represents. So how do you write this in interval notation? Well, you use a parenthesis, and we'll see that when you include the endpoints, we're going to use a different symbol, but when the endpoints are not included, use a parenthesis symbol. And then you put your smaller number on the left, your bigger number on the right, and another parenthesis. So it's always smaller number on the left, bigger number on the right. And I know, by the way, that this kind of looks like an ordered pair, right? This looks like you're talking about a point like x comma y. It's just kind of an unfortunate coincidence that the notation looks the same, but generally speaking, you should be able to tell which thing we're referring to depending on context. So, in this video, in this kind of context of finding domains, you should know that we're talking about an interval, whereas if you're talking about like a graph, then you might be talking about a point. So, I'll always try to make it clear which thing we're referring to with that notation in the future. Okay, so now let's say we are in a situation where we're trying to say that x is greater than a. So maybe we're finding the domain and we're like, oh, the domain is all numbers bigger than 5, right? That would be a situation where you could say x is greater than a. So what is that going to look like on a number line? Well, now we have our number a, and instead of having a right endpoint of b, we're just saying literally x can be anything bigger than a. So I'm just going to shade everything to the right, including the arrow saying everything bigger. So how would you write this as an interval? Well, this time there is no right endpoint. And so instead of putting a number as the right endpoint, you put the infinity symbol. Okay, similarly, if x is less than b, then we're going to have no left endpoint. So we have the number b as our kind of top number, and then we're just saying anything below that, any number less than b. And so how would we write this in interval notation? Well, we would say negative infinity up to b. And then the last one, so if we're saying x is any real number, so there's no restriction, there isn't really a great way to write that as an inequality. If you really wanted to, you could write it like this, but people don't generally write this as an inequality. You could say, oh, it's between negative and positive infinity, but usually you wouldn't really write an inequality. You would just say any real number. But it is, we do actually use interval notation pretty commonly in this situation, so I do want to show you that. And I think the number line kind of helps visualize it as well. So if we're saying that x can be any real number, well, that means that we need to shade the entire number line, right? Because that's like every number. And so how do you write that in interval notation? You say negative infinity to positive infinity. Okay, so don't worry if this seems all very general. We'll get into some specific examples in just a moment. I just want to first add a couple of important notes. So the first one is something we already mentioned. So if the endpoints are included, I'll say endpoints is or are included, because some of these only have one endpoint, right? So if the endpoints is or are included, then for the inequality, we're going to use the symbol, less than or equal to or greater than or equal to instead of just less than. And then the really important thing is for interval notation, you're going to, instead of using a parenthesis symbol, you're going to use a bracket symbol. And depending if it's the left or the right hand bracket, I'll kind of write both down. So this is really important. Maybe I'll highlight this, because I know I used to, when I made this table, I used to put this on the table as well, but then the table just had so much stuff on it. I think it got a little confusing. So basically everything that is already on this table, if you just change it to including the endpoints, then you're going to switch to brackets instead of parentheses. So one other thing that is kind of a side note to that is that when you have an endpoint, quote unquote, it's not really an endpoint, but if one end of your interval is infinity or negative infinity, you always use a parenthesis. And the reason for that is that there's no such thing as including infinity. Infinity is not a number. So the brackets are reserved for saying, for example, if you want to say x is greater than or equal to 2, well, then you would use a bracket with the 2 to say that you're including the 2, but you're never going to put a bracket with positive or negative infinity because those aren't numbers. They're not getting included in any way. So you're going to always use the parentheses with negative infinity and positive infinity. And one other thing, and we'll come back to this in a little bit, is that sometimes you're going to need to describe more than one interval at once. And there's a symbol that allows you to kind of group together intervals. So to list multiple intervals, so if you want to say, okay, I have this one interval and then I also want to include another one, you're going to use what's called the union symbol. And so the union symbol is literally just like a capital U. And so we'll see some examples of that in a little bit. Okay, so let's get into some examples. All right, so let's say that, for example, we wanted to, I'm going to give it as an inequality, and we're then going to rewrite it in interval notation. So we're going to express x is greater than or equal to 3 in interval notation. And actually, for all of these, and I think this is just like a good practice in general, especially as you're getting used to this, I think first doing it in number line, writing out on a number line, is a good kind of transition to help you go from the inequality to the interval, especially when we get to the more kind of complicated examples. So the reason I picked this example is because we actually saw this already, right? This was the domain for our function g of x, right? We said the domain was all real numbers greater than or equal to 3. Another way of writing that would be saying x is greater than or equal to 3, right? If we're saying the domain, x can be any real number greater than or equal to 3, that's exactly how you would write that as an inequality. And so if I asked you to write your answer for the domain in interval notation, that's where this table that we just made comes in. So let's start by, again, making a number line. So if we have a number line and we put the number 3 on it, and notice I'm actually filling in the point at 3 because this time we're including 3. So where would I shade if we want to represent all numbers greater than or equal to 3? Well, I shade to the right. And so how does this translate into an interval? Well, we want to use a bracket because 3 is included. And then our right endpoint, well, there is no right endpoint. And so we put infinity and a parenthesis. So this would be our answer of interval notation. Okay, let's do another few. And I would encourage you, if you feel like you really have the hang of this, to try these yourself. So let's express the inequality -1 is less than x is less than 10 in interval notation. In other words, we're basically saying x is between -1 and, interval notation. So we're basically just saying x is between -1 and 10. Okay, so what would this look like as a number line? Well, we would want to put the numbers -1 and 10. And when we go in and shade this, we're not going to include them. So we're going to leave open circles on -1 and 10 because there's no, we didn't have like an equal sign here. We just had less than. And so how would we write this as an interval? Well, we would say our left endpoint is -1, and we put a parenthesis because it's not included. And our right endpoint is 10. We put another parenthesis because, again, the 10 is not included. All right, one more kind of this style, and then we'll see something a little bit trickier. So let's say that now we wanted to express x is between 2 and 5, but notice that this time we're saying that x is strictly greater than 2, but it could be equal to 5, right? So one of them has just a less than symbol, and the other one has less than or equal to. Okay, so let's do this on a number line first. So we put down our number 2, our number 5. And now we can start to shade stuff in. So in this case, because 2 is not included, we want to make sure that we put an open circle on 2. But 5 is included, and so we would put a closed circle on 5. And so then we shade between them because x is supposed to be between -2 and 5. And so as an interval, this would say 2 with a bracket, 5 with a parenthesis. So the reason I wanted to show you this example is to show you can mix and match. Sometimes you can have a bracket and a parenthesis in the same interval. It just depends. Ooh, and I switched that. Sorry, my bad. So sorry if that confused you. This should be a parenthesis, right? Because 2 is not included. And this should be a bracket. My bad. So you can mix and match. Okay, so let's do, I lied, I'm actually gonna do one more that's kind of like this. It's again a little trickier, and then we'll jump to something that's a little bit different. So let's say we wanted to now express x is less than or equal to -1, or x is greater than or equal to 3 in interval notation. So this is a situation where we're going to have 2 intervals. And I think the easiest way to see that is by drawing it on the number line, right? So if we start by putting in our -1 and our 3, and notice that they both have equal signs. So when we go and shade, we're going to put a closed circle on these. So we'll put a closed circle here, closed circle here. But then if you look at what this is saying, the first one is saying x is less than or equal to -1. So that means we're looking at like this part. And then the other one says x is greater than or equal to 3. So that means we're looking at this part. And so this is not just one interval, right? If we look at all these other ones, so far they've all been just one interval. And this one is 2. And so that's where that union symbol is going to come in. So we just want to start kind of left to right and write down each of them. So the first one is going to be -infinity up until -1. And then we put a square bracket, right? So that's just the first interval. And then we use this union symbol to basically say, okay, and then we also have another interval. So the other interval, we use a bracket because the 3 is included, and then we say 3 to infinity. Okay, so far, this last one was kind of an exception, but these have all been inequalities. I guess the last one wasn't really an exception in the sense that it was an inequality, right? These were all either one or multiple inequalities. But what we saw was that in the previous video, we saw that sometimes when you're finding the domain, your answer wasn't an inequality, right? It wasn't like all real numbers less than something or greater than something. We had some problems where the domain was like all real numbers except for 5 or something like that. And so that's the type of example I want to look at now. Okay, so let's say that you're finding the domain of a problem and you find that x can be any number except for 5. And so another way of writing that would be x is not equal to 5. So this one, I think at first it might seem a little tricky to like figure out how would you kind of translate that into an interval. I think this is a really great example for how much the number line can help. Okay, so if we're saying x is not equal to 5, but x can be anything else, that means that we want to go in on our number line. We want to take that number 5, and we want to put an open circle around 5, right? Because 5 is not supposed to be included, right? We're saying x can't be 5. And that's what that open circle represents. But then if the only number x is not allowed to be is 5, that means x can be anything else. So we should be shading in this part of the number line. We should be shading in this part of the number line, right? We should be shading in like everything except for 5. And so if you think about it, this example is actually pretty similar to the one above because we actually have 2 intervals here, right? So the first interval is everything from -infinity up until 5, not including 5, right? So just maybe for a moment, just like kind of cover up the right-hand side and just think about the left-hand side. It's -infinity up until 5. And then we also have another interval on the right side. And so we're going to use the union symbol and then say everything from 5 until infinity. So this is how we can take, now basically everything that we talked about with domains in the last video, we've now seen how to write them in interval notation because we know how to change an inequality into interval notation. We also know how to change now something where you're just picking out one specific number into interval notation. Let's do one more example. And again, I really encourage you to try this yourself because I think hopefully at this point you have kind of gotten a sense of how this works. So what I want you to express, is x is not equal to -2 or 7 in interval notation. So this, we didn't do any examples in the video where this came up, but if you did the worksheet that went with the previous video, you should have seen there was one example where there were multiple numbers that made the denominator 0 of a function. So you had a domain where there are 2 numbers that weren't allowed. So that's why I'm giving you this example. Okay, so how should we do this? Well, definitely with this one, I think drawing the number line really, really helps. So we know that our numbers of interest here are -2 and 7. And we know that we are not including those numbers, and so we want to put open circles on them. But everything else is allowed, right? If we're told that the only restriction is that x is not -2 or 7, that means that everything else is fair game. And so that means we want to shade in everything else on the number line. So everything is shaded in except for -2 and 7. All right, so how many intervals do we have this time? Well, now we actually have 3, right? We have one interval here, we have a second interval here, we have a third interval here. Because these points -2 and 7 are removed, those are kind of the transition points between the different intervals. So let's just go left to right. So what is the first interval going to be? Well, it's going to be -infinity up until -2. And then we put a parenthesis because we're not including -2. The next interval, so now we put a union symbol, right? And then the next interval is everything from -2 to 7. And then the next interval is everything from 7 to infinity. And so we have 3 intervals and we kind of just connect them together with the union symbol. So yeah, so the main thing I want you to take away from this video, again, is basically just the mechanics of like, how do you translate this stuff into intervals? And the other important thing that I just want to mention again, because we talked about it at the beginning, but it's been a little while, is this difference between our initial examples and our later examples, right? So at the beginning, we saw an example where the domain was just like 3 specific numbers, and that was it. In all of these examples that we just did with different interval notation, every single one of these intervals represents infinitely many numbers, right? So I want you, when you see an interval, to think of it as meaning, so like, for example, this first one, or actually, let's look at the second one, the one in blue. This interval represents every single number between -1 and 10. Not including -1 and 10. And so that's not just numbers like 1, 2, 3, 4, 5, 6, 7, 8, 9. That's also all of the decimals that lie in between. So there's a really big difference between writing down an interval where you're really meaning every single tiny little different number between those 2 numbers versus using the set notation at the beginning. This kind of notation means just these specific numbers, whereas the interval means everything in between. All right, so as I said, in the next video, we'll finally bring this all together and see how to start to finish, find the domain of a function and write it in interval notation. So I'll see you all in the next video.